So let's talk about acceleration, average acceleration, and acceleration in general, with respect to graphs. So the first kind of graph I want to talk about is the one we did in the previous lessons, distance or displacement versus time. I tried to recreate that graph from the previous examples, and on that graph I put in some average velocities that we had calculated before for certain segments of the graph. Right? We said for this segment, you're not moving, so 0 meters a second. Here, we have a positive 2 meters a second. Actually, positive 1 meter a second. My apologies. Going on here. And for here, let's double check. I go from 4 to negative 4, so that's 8 divided by 2 seconds, so that should be a minus 4 meters a second. Those are the initial, the first couple velocities on the segments of this graph. We discussed that yes, over here we can have an average velocity, but we don't know any individual or instantaneous velocity because it's all wonky. We could find instantaneous velocities, of course, if we did tangent lines, and we had that same discussion over here. But I just want to focus here. Because I could be asked, well, what's the acceleration average acceleration within certain time intervals? Now remember, average acceleration is delta v over delta t. And I can interpret this graph to get some of that information. If I were to ask the average acceleration for the first second, well, I'm not moving at all. And if I'm not moving at all, I'm not changing velocity, and so therefore there would be no average acceleration here. There's no speed, there's no acceleration. If I were to be asked the average acceleration from position 1 to position 3, or time 1 to time 3, the first and third seconds. Note, this is a constant speed. It's nice and constant. The speed isn't changing because the slope isn't changing between 1 and 3. And so if the slope isn't changing, if the speed is constant, the speed is always 1 meter a second for every moment along this segment of the graph, there also would not be a change in velocity over time. You would have no acceleration on this segment. The same thing would go here. From 3 seconds to 5 seconds. Between 3 and 5 seconds, it's a constant velocity, although negative. And because the velocity isn't changing every moment to moment to moment, acceleration again. And there wouldn't be any. You're not changing speed or velocity. Now, in here, there are changes in speed. But we don't know what those initial and final speeds are unless we were doing some tangent lines, which I'm not going to ask you to do right now. So finding the initial and final speeds here and finding an average velocity could be done. It would be a mess. And even so, because the velocity is so random, the accelerations contained in this traveling would also be random. You could find that average acceleration, but it really wouldn't tell you much with the shakiness of this motion. Now over here, it's a nice parabolic shape. And what we're going to learn is that if we see nice parabolic shapes, whether they're up like this or down like this, or even other graphs are going to go up like this, when you see a nice parabolic shape on a distance time graph, that is telling you that there's an acceleration. And it's probably a nice consistent or constant acceleration. Now, I can't calculate what that value is off a distance time graph by using just this data. But if you found a tangent and an instantaneous velocity at one point, and an instantaneous velocity at another point, and maybe another instantaneous velocity somewhere in the middle, and we're to take those instantaneous velocities, find those velocities at those times, you could then, therefore, solve this. You could plug those in. Feasible, yes. I'm not going to do an example here. I'm just saying that it could be done. And we may in class do one or two of these, but really, there are, if you take higher physics classes later, there are other ways to solve for that. And even in this course, in a few days, maybe not graphically, but we'll find other ways where we can determine that information. You could get some weird question, say what's the average acceleration between like 0 and 5 seconds? And we could do that because at 0 seconds, well, we know the speed at 0 seconds is 0 meters a second. We know the speed there, or the velocity, nothing. So, and at 5 seconds, we do happen to know the velocity. It's just the end of that -4 meters per second segment, and so that speed translates at that point. Or we can, clearly say that, all right, we're gonna let that happen, because right at that point we're changing motion. So, the moment before 5 seconds, it was at -4 meters a second. The moment after 5 seconds, the motion may be changing, but as we approach that 5 seconds, we can say that this value is valid as an estimation. And we know that took 5 seconds. And if you do this, you're going to end up with -4/5, which is going to be -0.80 meters per second squared. So it's going to be rare that you're forced to read a distance time graph for acceleration information, but you should be able to identify, just by looks, when certain segments of a distance time graph have acceleration and do not have acceleration. So no acceleration, not moving, no acceleration because you are constant velocities. Curvature, especially nice parabolic curvature. Yes, acceleration. This is wacky acceleration, not constant. This is probably nice and constant acceleration. Okay? All right, next segment we're going to get into the velocity time graphs and how we're going to interpret them for acceleration. And we're going to interpret them for finding distances traveled. Hang on.